Hello, everyone. We are going to let everyone kind of stream in from the waiting room into the webinar room and get started in a couple of minutes. So just give you a few more minutes to let everyone come in. Okay, well, I'll get things started here. Just want to say hello to everyone and thank you very much for joining us here this afternoon or this morning, wherever in the world you find yourself today. This is the third in a series of webinars brought to you and to us by Mitsubishi Electric Heating and Cooling. My name is Ken Lascastle. I'm the Chief Operating Officer with the Mechanical Contractors Association of Canada. And I'm very pleased to be joined here today by Stephen Cornelius, who is the Business Development Representative HVAC Division with Mitsubishi Electric Canada. As we all know and can appreciate, there's a lot of discussion these days concerning the role heat pumps are going to play, specifically in this transition to net zero in the built environment that we're talking about so often these days. Since heating and cooling play such a significant part in the energy usage of a building, there's a role for this technology and heat pumps that they can play in reducing that energy usage and ultimately greenhouse gas emissions from the built environment. We know this is a very pertinent topic and very pleased to be having you join us here today. Before I turn things over to Stephen, I just want to let everyone know that we will have time for questions and answers after his presentation. I would encourage you to use the chat function on the bottom of your Zoom screen or the Q&A function. And we'll keep an eye on that throughout the meeting and the presentation. And when we turn things over to Q&A, I'll pose those questions to Stephen on your behalf. So again, thank you very much for joining us. And Stephen, the floor is yours.
Thank you, Ken. And welcome attendees. Okay. Are you seeing my screen?
Yes, we are. Yep.
Okay, marvelous. Oh yeah. Perfect. Okay. So again, my name is Stephen Cornelius. Thank you for having me. I am glad to be here today. I will say you're in for a bit of a treat because usually I have canned presentations and I just wash and repeat over and over again. And so this one I actually created from scratch because I wanted to make sure that I have new information for people out there. So let's get started. So Mitsubishi Electric Canada, we go by the name of MESCA, which is an acronym for Mitsubishi Electric Sales Canada. We're a Canadian subsidiary of Mitsubishi Electric in Japan, and we've been here since 1979. And we like to be involved in sustainable initiatives. So we're involved with many organizations such as obviously Mechanical Contractors Association, CHBA, CAGBC, Active House Canada, Passive Buildings Canada, Inequality, TRCA, HRAI, and NRCan. So all that to say that, you know, it's really in our ethos to be a purveyor of environmental solutions. Please forgive my next slide. I couldn't come up with any better imagery, but all that to say, over a decade ago, when I first heard about the plan for electrification, you know, I thought, what was our government trying to do to us? I'd always been used to gas heat, and I knew electric heat was ridiculously expensive. So how are they talking about moving us all onto electric heating? It was obviously going to be more expensive, and this must have been just another way to suck the money out of the people. Now, I knew about commercial VRF systems, but I really didn't have a lot of knowledge of residential systems. And to be fair, you know, many years ago, residential systems weren't really known for their low ambient heating capabilities. So now in the time since, we've all found out the reason for this push for electrification and it's decarbonization. And so we should all be familiar with this term by now. We hear it every day. You know, it's eat into us day in, day out. But why should we decarbonize? It's because of when we burn fossil fuels, it creates the byproduct CO2. And this in turn collects in our atmosphere and contributes to warming of the earth. Now we can get into a long debate about who and what and where are the most and worst emitters, but we're not here for that. And so let's just stick to what we can affect. And between commercial buildings and residential buildings and institutional buildings, they combine for 20% of GHG emissions in Canada. So put together, the building sector accounts for the largest sector of GHG emissions. So that's why we should care. Now, every level of government, utilities, the provinces, cities, nonprofits have all published a steady stream of studies, go back across the years. And, depending on where you live, you can find a study from your local governments that report on strategic electrification and the best ways to achieve their aggressive carbon emission reduction goals. So installing an air source heat pump in 50% of the residential and commercial buildings could reduce our GHG emissions by almost 30% as compared to our business as usual way of going about life. And to further encourage the transition, we have the carbon tax, which will increase the price per ton $15 per year up to $170 per ton by 2030. Now, this will double the consumer cost of natural gas, and this improves the business case for making changes now for all entities, especially larger entities that are using a lot of natural gas. And so, looking at these charts here, you can see the growth of the increase, in the carbon tax, which will get us up to 170, which is only in 7 years. And, on a residential side, you can see from 2019 to 2022, we've already gone up almost $4 per cubic meter. And this ties into my next slide, where we're looking at the operational costs of heat pumps. So many of you who've been in the business for many years, I'm sure you've told people that the cost of running a heat pump is going to be, exponentially more than your gas, and it's not worth it. But it ends up, it's not really true. I mean, there was a time, yes, because they couldn't compete with the low ambient performance of a furnace. But this chart here is an excerpt from a Natural Resources Canada report that was done in 2020, and it looked at comparing heat pumps to electric resistance heat and gas furnaces and oil. It didn't touch on propane, unfortunately, but this report is readily available online. It's a long read, but it really sorts out and does it clearly that heat pumps, at least in 2020, were right there. Looking at this chart here, this lists all the major cities in Canada. And if you take an Archetype B home, which is a post-1980 gas home, and you switched out your natural gas for a heat pump system, in the majority of cities in Canada, you'd actually end up ahead. Only Winnipeg and Prince George would you be in the red. And so now if you take into account the increases in gas costs, those two red cities will be a little bit lower, and you'll definitely be better in the other cities. So this is the cover page for the report that the chart was from. Like I said, it's available for download. The link's right here. It was done by Jeremy Sager and his team, his CanMet team at Enercan. And like I said, it's a very comprehensive report. And it goes through, again, all the cities, or all the major cities in Canada, and the operational costs based on 2020 pricing of energy. And part of that was with fixed pricing, which we don't have anymore. But again, it still really illuminates how close heat pumps are and how they will easily surpass natural gas in the near future. And just throwing this one in here for the people on the East Coast, if you have an oil furnace, or anywhere in the country, if you have an oil furnace, you're by far ahead to get off oil and move into a heat pump system, whether it be ground source or air source or water source. And propane will be similar due to the increases in costs there. So as you may have heard, air source heat pump technology consolidates heating and cooling into one all-electric system. So it can be either a single zone or a multi-zone system, and it can be used in offices, hotels, schools, multifamily buildings, indoor agriculture, or practically any commercial or residential application you can think of. So these are just some images: hotel, top right, a multi-unit residential building, bottom right, via station, bottom left, and a church, top left. So an air source heat pump system consists of an outdoor unit and up to 8 indoor units if you have a multi-split system. And they're connected via refrigerant lines and communication network. Indoor units are available in various ductless and ducted styles. And of course, the selections and combinations will vary by brand. Just to point out here, up on the top on the right there, that's a coil that we have so that connects to an outdoor unit where that can be paired with a gas furnace. And we'll touch on that later. So when you look at multi-zone systems, each zone is conditioned by its own indoor unit and can have its own set point. So this is very valuable, really in most homes, but anywhere where you have multiple levels, so 2, 3, 4, if you have one of these tall, thin townhomes, and obviously a house that is spread out across a big platform, with the long duct runs, that farthest room is not getting much heating or cooling. And if you were to use a multi-split system now, you could have a head that supplies thermal energy to that room specifically, and you can control the temperature for that room. And or if you just did a one-to-one, say that room over the garage there, which are typically cold because they're not well insulated from the garage, again, you could temper that room separately from the rest of the house. And so obviously, we're here talking about heat pumps, and they're a key solution to decarbonizing because obviously instead of burning fuel, they provide heating by capturing heat from outside and transferring that through the refrigerant lines to the inside units, and vice versa, capturing heat from indoors and moving it to outdoors in the cooling season. So this is a crazy looking chart. And so whether you believe the hype or not, the data here shows that heat pump sales in Canada over the past 2 decades have increased exponentially. So since 2000, heat pump sales have increased by nearly 6 times, from 65 million to 1.05 billion in 2020. And it's still going up every year. So this is an increase of 15.4% each year. And then between 2007 and 2020, the market has grown by an average of 11.2% each year. And the highest growth was seen in 2017 at 17.7. The highest sales are basically by population density. So in Canada, we have Ontario having the highest sales, followed by Quebec and British Columbia. And then the other provinces trail after that. Overall, heat pump sales have been steadily increasing, and we see the trend continuing because heat pump systems are getting better and better. And obviously, there's more players coming into the market as well, so people are having more choice. Now, these numbers, increased sales, are being matched and exceeded in Europe and US, where heat pump sales for the first time have passed boilers and gas furnaces in the respective countries. Now, you can't have a conversation today without talking about energy efficiency. And when we're talking about heat pumps, we're comparing them to all other forms of heating and cooling. So heat pumps, whether air source, water source, ground source, are the most energy efficient for thermally conditioning a space. And following on that, there's no more efficient way of transporting thermal energy than refrigerant. Think about how much space ductwork takes to move conditioned air adequately around a home. Water and refrigerant lines are much more, water and refrigerant are much more dense, and they do a better job of carrying thermal energy to various spaces. So on this image here, when we're looking at 20 tons of cooling, you need a 36-inch diameter duct. Compare that to the water pipe and the refrigerant lines. And imagine how differently you could put together a space if you didn't have to account for all the ducting and the size of the ducting and the space that it would take. Now, I've been told this chart has really helped some people understand how heat pumps make sense in our climate. This is a chart depicting the efficiency curve for a 3-ton Zuba system, and it's being compared to conventional heating systems. So we have electric resistance heat in the blue, we have natural gas in yellow, and oil in black. And of course, their efficiencies don't change. So your electric resistance is going to be effectively 100%, or a COP of 1. Your natural gas, 95, 97, so a COP of 0.95 or 97, and oil, slightly below there. But again, straight lines, not dependent on the weather. Now, heat pumps, of course, are affected by outdoor ambient temperatures. So the green line there, has a declining slope. But what is really important to look at here is the percentage of time that we spend at the low ambient temperatures. So again, the common thought is, well, heat pumps, they're not going to be able to handle, negative 20 or negative whatever it is in where you live. But look how much time we actually spend at these low temperatures. We don't ever really sit at these low ambient temperatures for very long. So when you take the average over a year and, calculate it out, and we'll see it in the weather data in the next few slides, below negative 15, 0.5%, in Southern Ontario, say. Between negative 10 and negative 15, 1.8% of the year. And negative 5, negative 10, 5.5% of the year. And, you're still at above a COP of 2, which is double what any of the other systems can do. Oops, sorry. Let's see, Toronto. Okay, so here's weather data for Toronto, and I'll go through a couple other cities. But looking at the 3-year average of weather data, evidence shows us that 98% of the year is spent above negative 15 C. So if you size your system that can deliver 100% of the required capacity at negative 15, you're still above a COP of, at least 1.5, and that's 50% better than the next alternative. And you may have a system that's even more efficient. So maybe you're a COP of 2. But again, the majority of the operating time, your system is running very efficiently. Here's the weather data for Ottawa. 3-year average. Evidence shows here that at 96% of the time, you're spending above negative 15 C. And so, speaking for Mitsubishi, our systems will give you 100% at negative 15. So for 96% of the time that the system is running, it'll be giving you 100% of its capacity, or the ability to give 100% of its heating capacity. Montreal, 3-year average, 97% of the time you're spending above negative 15 C. And then lastly, I picked up Edmonton, because obviously it's a lot colder there, but still looking at 3-year data, 90% of the time of the year, you're spending above negative 15 C. So the following slides here are just to demonstrate COP as it relates to systems in a home. So in this diagram, we have a condensing furnace, we'll say with a efficiency of 9.95%. Obviously, it can never be 100 because it's going to have losses to heat and light. When you take into account the electrical consumption, then it drops down. So you end up 91% efficient, or a COP of 9.1. Here, the depiction is of an electric furnace or electric resistant heat. So, effectively 100%. So a COP of 1. And, all three of these are at negative 15 C. And here we have a 3-ton cold climate unit. So the efficiency of the heat pump at this point is 186%, based on the amount of energy that is being captured from outside, transferred inside, and the amount of electricity that is being used to make that transfer. And so at negative 15, the system's still at 100%. Oops, sorry, I can't advance here. So again, just to point out, the system only uses the electrical energy to run the fan, run the compressor, obviously run the circuitry, but the refrigerant is doing all the work, transferring the heat from one space to the other. And so that is what makes heat pump systems so efficient. So now let's look at indoor air quality. Now, I think this should be a far more important feature in the acquisition of a home. With all the respiratory illnesses, asthma being the most common, I think this should be a really primary concern, but it's not something that's brought up a lot. ASHRAE 62.1 deals with ventilation for acceptable indoor air quality. But what about the off-gassing materials in the home? What about gas appliances releasing toxins in the home? Now, is anybody aware that's even a thing? Your furnace exhaust must be at least 3 feet away from any window, door, or intake. Yet if you have a gas stove, there's no interlock on the hood. You can start that gas range top and cook whatever you need to cook, and now all that exhaust is being circulated in your home. And I've had a natural draft water heater, and it's just basically got a little capture hood over the top, but I'm sure there's a portion of that that's escaping into my house. So now if you went to an all-electric system, this is not even a concern. And this article here was done by the CBC, and it states that gas stoves produce more indoor air pollutants than anyone expected. And this follows a concerning study published by a professor at Stanford earlier last year. And it stated that gas stoves leaked unexpectedly high levels of methane, even when off. On top of methane produced from this combustion, we have nitrogen dioxide, formaldehyde, nitric oxide, and carbon monoxide. Now, I know, from a home builder standpoint, many people want the gas stove because that's just the creme de la creme. But really, when you think about indoor air quality, the hoods do not do a great job of capturing that exhaust. And we plumb exhaust out from our furnace, from our gas fireplaces, like, none of that is supposed to escape, but yet, you have a gas fireplace and it's leaking right into the home. Just something for thought. Yeah, I already mentioned the hoods and natural gas furnaces. Well, yeah, in 2015, Health Canada issued new residential air quality guidelines, but somehow gas stoves were never included, as they are the worst offenders. So something to think about. And let's talk about leaving air temperatures and how it relates to indoor air quality. Furnace heated air coming out of the vents of your home are around 50 to 60 degrees C. And do you really need it to be that hot to get your home to 22 C? Now, even if you set the thermostat higher to say 24, you could still heat your home using 35 C air. Of course, when you add warm air to cool air, it's going to equalize and get you to your set point. And so with a heat pump, they obviously deliver a lower temperature air, But because of that, they have to deliver more air. And so that gives you more air circulation. And that, of course, gives you more filtration of the air. So you're getting better airflow and essentially better air quality. And then on top of that, when you have hot air coming out of a register, it's going to stratify. So it's going to, go up to the ceiling. It's hot air. That's what it's got to do. And if you have a multi-level home, then most of that hot air is going to go right to the top, and there's not going to be much in the bottom. If you use cooler air to mix in to get you to your set point, you have much less stratification. You have much better mixing of air because the temperatures of the two airs are not, the delta T is not very big, and so you have better mixing and less stratification. So overall, cooler distribution air temp is much better. Now, the application of heat pumps and where they go. So whether it's an apartment or townhouse or a detached home, central air handling unit would take the place of a conventional air handler, whether it be furnace or electric, whatever it may be. And it can provide you your conditioned air through the existing ductwork in a retrofit application. Again, the difference is that now you don't have GHG emissions and you will have more airflow. Spoke about the multi-split systems. And again, in an ideal world, they're a better setup because now you can have different set points for each space. And they come in obviously of various of sizes, various of indoor units, depending on the application. But they are the ideal way to go if you're able to go with a multi-split system. So now we have hybrid systems. For those that are on the fence, you want to hedge your bets. And really for the population at large, we have 37 million gas customers in Ontario, right? So heating their homes with gas. There's no way they're all going to switch over to electric, and it's not practical, and our system couldn't handle it anyway. So then, you have an ability to have a hybrid system. So I have builders in Calgary, Ottawa, some in Ontario that use a hydronic coil on top of an air handler. So ideally you use an air handler that is not cold climate because you already have the ability to give you that low ambient heating through the hot water coil. So you go with a standard unit and you pair that with a hydronic coil that's fed from any way you want to heat the water. And the systems can work together so that the heat pump will work down to a certain set point, and then you switch over to the hydronic coil and you get the best of both. And we've worked with direct coil to manufacture case coils that sit on top of our air handling unit. But obviously, whatever coil you use should be sized for the airflow and the water flow for the system that you're using. But really not complicated. The systems work well together, and it's a nice transitionary system. And some specific details on the coils that the Ottawa builder is using. Now this here is a coil that's attached or combined with an outdoor condenser, and this can be paired on any gas furnace. So again, the concept is, you already have an existing gas furnace, your air conditioning coil has gone on the fritz, and you do want to try to reduce your GHG, but you've got a good furnace, you're not going to throw it out the window. So you pair it with heat pump A coil, and now you have the best of both. You have systems that, this particular system here can communicate with the furnace and control the set point changeover. And if it's paired with a cold climate system, you should be able to go down to -20, -25, depending on what the heat load is, before you switch over to gas. Even if necessary, maybe it just runs on heat pump alone. But this is, again, another way for people to transition to electrification. So considerations. When you are looking for heat pumps. HSPF is probably the most important thing, because this shows you how well the unit performs in low ambient temperatures. And this is very similar to the AFUE. The higher the percentage, the more efficient the unit. So HSPF can range from 6.8 up to about 13.5. And the lowest HSPF rating for heat pump to be Energy Star considered is 8.2. And this is with the M ratings. We're now switching to M2 and 8.5 for split systems. Now, I know most of you are used to looking at SEER ratings, obviously for the cooling side, but heating is much more important. It's the bigger factor in Canada. Many products claim that they work down to -25 or -30, but you really got to look at what percentage of their output are they giving at those low ambient. So at -15, are they at 80%, 100%, or 50%? Because that really determines if it's a good match or a good solution for what you're looking for. Other things to consider, is it a true variable speed? Parts and availability. Is it something that you can repair, 10 years down the road, or is you just going to toss it and replace it? And then, of course, your sizing should be based on the heat load. And so in that aspect, there's many solutions for you. There's many resources. And one of them being this toolkit that Enercan has created and is available for download. And it helps you size and select heat pumps based on a series of inputs that you put in and charts and graphs. And the other alternative you have are energy advisors. There's many of them out there. They're doing audits for the Greener Homes Grant, but at any time you can reach out to one, you can partner with one, but their essential goal is to go in and evaluate a house and do the heat load calcs. And then if you're doing a new build, there are a plethora of HVAC designers that are out there that will, again, give you I would say, accurate heat load calculation on a planned bill based on the materials that are going to be used, the envelope, the windows, insulation values, all the rest of that. And then that can help you accurately size a heat pump for those projects. And I've come to the end of my presentation. I'm opening it up for questions. And I hope that you found this informative.
Thanks, Stephen. Keep an eye on the questions, see if anything comes in. Just to kick it off, I would have one for you, if you'll take it. You talked a little bit earlier on in the presentation about the types of buildings that are suited for heat pumps, and you alluded to that heat pumps can essentially work in any built environment. From your perspective, are there certain building types that are better suited for heat pumps? And I think the second part of that is on the retrofit side. Are there certain buildings that will need to be retrofitted that are better suited for heat pumps as well?
Well, on the suited side, I would say the less leakier, the better. So, if an envelope improvement needs to be done, that probably should be done because that just helps. But you have the choice of having, a split system or a central system, which is, VRF or commercial. With the split systems, obviously you have to have a place to put the condensers. And so you have a limit with the line length, the refrigerant line length. So something that's maybe max 4 stories tall, you can put them all on the roof, if that made sense, or you can put them on the ground and you should be able to reach all the various spaces. If there's balconies in a residential application, that could work, but sometimes aesthetics, that's a problem. But then for everything else, you have the central units where you have a much larger, 3-phase system with a condenser that, again, could be put on the roof or on the ground, with much longer runs. And then, with refrigerant lines, you can run them through existing chases, obviously, if there is any, or they can be run on the outside of the building. But as far as, an ideal building, really they'll fit in any building, because with most buildings you have a lot of duct work, you already have chases, and then if it doesn't have any of that, if it's all electrically heated, then it's as simple as running refrigerant lines with an indoor head in that space.
We had one question come into the Q&A. It's how do you see unit lifespan impact with more runtime versus current AC usage in Canada?
Well, I can only speak from our standpoint, but we have systems that are in the field over 20 years. Again, over time, fans have gotten better, bearings have gotten better. These things are built to last 20, 25 years, which is, I think, typical lifespan for a lot of HVAC equipment. So don't see any issues, because they're designed to run, more than less.
From a skill set perspective and a training perspective, what types of skills do you think are going to be critical for contractors to have, excuse the pun, in their tool belt when it comes to the installation, service, maintenance of this technology?
Well, to be frank, a heat pump system is a refrigerant system, and so people that have installed AC, are familiar with the technology and refrigerant lines and pressures and whatnot. And if they're not, they should look to get trained in refrigeration. In the coming years, we're going to see a change in refrigerant, which is going to increase pressures. So a lot of people will need to get retrained in that regard. And if you can take an HRAI course on load calculations, that definitely helps, because then you don't have to go to a third party to get a heat load calculation for you. You can actually, do it yourself and be a one-stop shop for your customer. And as far as service, again, speaking about our systems, the boards are easily replaceable. If that were the case, there's good service support, where you can get to somebody on a phone, and they can walk you through any error codes that you may see, what that means, and how to come up with a solution. The biggest issue really for heat pump installations are leakages. So if you pressure test it and do the install properly, the systems will run well. I think there's about a 1% default rate on systems, so they're really reliable when they're put in properly. If you take the training, follow the manual, get your head wrapped around what you're doing, and be diligent, these systems run very well for a very long time.
Well, Stephen, I'm not seeing any other questions coming in at this time. So on behalf of MCA Canada, I just want to say thank you again for the presentation. This presentation was recorded, so we will be posting it up on the website. And if there are any questions, I would encourage attendees to reach out to MCA Canada, and we're happy to forward those on to Stephen and the Mitsubishi Electric team. So Stephen, thank you again for taking the time today, your expertise and your insights. And to those in attendance, thank you very much for joining us. Have a great day.
Thank you all. Have a great day.
Bye for now.